Hello and welcome to the lecture Neural Network Fundamentals Multi-Layer Perceptron. In this lecture, we are going to introduce multi-layer perceptron, then what do we mean by activation function, and what is the meaning of softmax activation function. In the last lecture, we have said that a single layer perceptron cannot solve a problem which is not linearly separable, like XOR problem. Now here we try to understand the how a multi-layer perceptron can solve it and why, where the basic strength of multi-layer perceptron. Essentially, by this particular problem, we understand why multi-layer perceptron, where there is a hidden layer, one or more than hidden layer, in between input and output layer of a neural network. Now see here that we have the XOR problem like this. So here we have this XOR problem. These two are 2 points, these two. And so there is no definitely single linear separator. Now here this is the a multi-layer perceptron. And what we can understand here, there is a hidden layer in between the input and output layer. For single layer perceptron, no such hidden layer was there. Now, how it helps? That is very important to understand. Now, this H1 is defined by this X2, this, and not of X1. This is H1. And what is H2? There's this X1 and not of X2. This is defined. And from our concept of the single layer perceptron, it can easily be done. And now what is Y? Y is just H1 or H2. This is from here, it is another single layer perceptron, you can see. So it can easily be realizable. And not means 1 minus x. So essentially, if we put that mathematically this formulation, H1, this is sigma is basically a sigmoid and nonlinearity of 1 minus x1, that is not of x1, plus x2. That means if we put a same thing here, minus 1 into x plus x2 plus 1, some similar thing. H2 is basically the sigma of x1 to 1 minus x2 is basically similar to that. If x1 plus minus x2 plus 1. So these are basic understanding of this H1 and H2. Now what is Y? Y is basically a simple odd function. So sigmoid of H1 or H2. So H1 plus H2 plus 2. So in this way, we can understand simply adding a hidden layer between input and output, it can solve this problem which is not linearly separable. So now only thing is that a multi-layer perceptron with a proper weight can predict the output of result which is not linearly separable. And this sigmoid function, as we know that this is like this, s of z equal to 1 by 1 plus 1 by z. And this is basically. So that what we can understand. Here this slide is very important because that we can understand the strength of hidden, the advantage of putting hidden between the input. Now we define multi-layer perceptron. In short, it's called MLP with one or more hidden layers. The strength of multi-layer perceptron lies in its hidden layers. That is understood in the previous slide. So neurons in the first hidden layer create multiple hyperplanes that partition the input space into several half spaces. Now this sentence is bit involved. Now here you can show some figure. Now here you can see this is the first hidden layer, and it basically, this is the input space, is a two-dimensional space. So hyperplane means it's a straight line here, and it creates two halves. Exactly, this is neurons in the first hidden layer create a multiple hyperplanes that partition the input space several half spaces. Exactly here, that is several neurons, so several partitions can fit. Okay. Now neurons in the following hidden layers combine these half spaces to form more complex regions. Now this is also very easily understand. Now if we adjoin these half spaces, these lines, it give you this. We can see that the first hidden layer cannot make this kind of triangular or kind of complicated shape. But if we adjoin this, then we can get such a complicated shape. And that is the basic strength of the multi-layer perceptron. The intersection of these half spaces produce convex regions such as polygons in two dimension or polytopes in the higher dimension. That we have seen that these are the polygons what we have achieved, or this can produce in the subsequent hyperplanes layers. The output layer combines these convex regions through unions, enabling the formation of complex decision boundaries that may be non-convex or even discrete. And that is the basic strength of multi-layer perceptron. This capability to construct intricate piecewise linear decision boundaries makes this multi-layer perceptron the universal approximate. That means this kind of capability, that piecewise linear decision boundaries, which make the NLP to an universal approximator, means most of the problem can be modeled by this, allowing them to approximate any continuous function when provided with enough hidden neurons and suitable activation. So that what is important here, that with this kind of structure, this is, I show you in one hidden layer, this may be multiple hidden layer, more than one, and this strengthens this neural network to solve a very complicated problem. Okay. Now here you can see that this particular problem, how we already discussed this problem, that how actually these hidden layers are here and facilitate to model more complex kind of plane or hyperplanes. Now we're going to understand the basic architecture of multilayer perceptron. As we have said, multilayer perceptron have one or more hidden layers between input and output layer. Here you can see here the k number of hidden layers between input layer and output layer. For understanding, we said that these are the inputs I0, I1, I. So these are the inputs. Then this is going to the hidden layer with n number of nodes. So this is the first hidden layer. And such k number of hidden layers. H of k1, H of ki, so. And this is now. So this is the basic architecture of the multilayer perceptron. Now we try to understand what are the jobs or what are the tasks of different layers. We start with input layer, that it acts as an entry point of the network. It simply receives the input features and forwards them to the next layer without performing any computation. So it basically take the inputs and forward it to the next layer. There is no computation is done. Second is come the hidden. It processes the input data and learn underlying patterns. Now the question is that here we can understand that there is several hidden layers. Although we are now discussing a simple multi-layer perceptron, we try to understand one thing here. The initial hidden layers in general try to model a very primitive patterns, since we are basically dealing with our vision problem. So pattern like straight line, slanted line, vertical line, horizontal line, simple curve, etc. When we are going to the more and more hidden or deeper layers or close to the output, these layers actually going to implement the more complex feature. Deeper the layer, more complex features to model. So this is the basic understanding. Even when we start the deep learning, that is also a very important concept, that we try to model or we try to extract the features at a different layer of abstraction in the different hidden layers. And that is most important understanding of deeper network. Here also, that in hidden layer, they process the input data and learn underlying patterns. And the primary layers or initial layers that basically try to understand or try to model the primitive patterns. Now, when it go to the higher layers, it tried to model the complicated ones. So these hidden layers allow the network to solve problems that cannot be separated by that we already have seen in case of software. Even a single hidden layer can represent complex relationships, while additional hidden layers increase the network's ability to approximate highly complex functional data. So this is the basic role of that. Finally, our output layer, the final processing layer of the network, and it combines the learned information from the hidden layers and generates the predicted. So we understand what are the basic role of input layers, hidden layers, and outputs. Now there is another very important concept, what activation. Activation functions introduce basically the non-linearity value, enabling the network to learn the complex pattern, like sigmoid activation function that we already been done. Now one question can come in the mind that if all hidden layers use a linear activation, this is what it is kind of function. The entire network behaves like a single layer model, regardless of the number of hidden layers. And this is a very important observation. This is because the multiple linear transformation combine into one single linear. So we have to put some sort of non-linearity. Just for example, the sigmoidal non-linearity. This sometimes called logistic function, the output between 0 and 1, commonly used for binary classification. It is differentiable but prone to vanishing gradient. So what about other activation function? That is hyperbolic tangent, it's called tan H function. This is basically a shifted version of sigmoid function. It is differentiable, but it suffers from the vanishing gradient. What is vanishing gradient? We'll come later. Then next come the ReLU, the rectified linear unit. This is faster and computationally efficient. It reduces the vanishing gradient problem for positive inputs, this part, but it can suffer from dying ReLU because it becomes 0 of its shade is less than 0. Then some alteration or modification of ReLU is called leaky ReLU. The variant of ReLU allows a small gradient for negative inputs. So it solves this dying ReLU problem and it somewhat solves some vanishing gradient issue also. Next comes the softmax activation, basically used in the output layer of neural network for classification tasks. It transforms the raw input scores, the logics, into probability values by normalizing them, ensuring that all outputs lies between 0 and 1 and their sums like this. If this is this output layer values, it uses the softmax activation a to the power zi by sum it up k j is equal to 1 to k to the power g of c. This softmax activation. So this it converts logics into probabilities like this, and in the output values range of 0 to 1 and so on. Since it's a probability like values. Generally used a final layer of classification network, and it's suitable for multi-class classification, but exactly one class is chosen. So this is a software. Now we try to understand what are the multi-layer perceptron with multiple ending layer, how the forward process. Now, as before said that this multi-layer perceptron has k number of ending layers, and P is the layer index for the input layer. P is production. So this is the bias one. So layer pre-activation is A of P of I, Vp plus Wp Hp. So this basically the before using the activation function, this is the solution. And what hidden layer activation is equal to 1 to k. H of p I j is g is your activation function, is the summation, and the output layer activation is equal to k plus 1 is basically so k plus 1 of 5 at O of. These are the basic functionalities, mathematical function. So in this lecture, we introduce multi-layer perceptron and try to understand the strength of the multi-layer perception over SLP by means of hidden layers. Then we discuss different activation layers and softmax activation. In the next lecture, we continue this, the training of multi-layer perception. Thank you very much.